Well, what I plan to tell you today is extremely down to earth, and the idea is that I presume that you know number theory and algebraic geometry, and I do not presume that you know anything about coding theory, sphere packings, and the like. So do I. I learned something about these objects which I call discrete, though it's not always that they're discrete, after I did my first work on the subject. And so that should be very encouraging, because you do not really need to be deep in the theory to do something in it. Your knowledge of number theory is much more important. And to start with, so we're speaking about coding theory. So it shouldn't be confounded with cryptology. These are two different subjects. So when we're speaking about a code, it is not a cipher, it's an error correcting code, a code that helps us to protect information in the sense to transmit it, and so you'll see. While I'm speaking to you right now, I hear some echoes. My pronunciation is not very good. I stumble, but nevertheless you understand me, I hope. Why? The reason is that the natural language has a lot of redundancy. That is, that the number of, the quantity of information measured in bits in a sentence of a certain length is much smaller than just if you write out 0 and 1s, and so to see if you want to compress what I'm saying, it is very much compressible. But because it is not compressed, it's redundant, you understand me. And there are funny mishearings from time to time, because the redundancy in a natural language is such that there are, however, words that resemble one another, and you may all of a sudden hear something which I was not going to see. But now, after the information started to be transmitted, which is by technical means, I mean, by radio, by telephone. The question became a question of technical importance. And this question of technical importance, let me put it in the following way. You have a certain alphabet A of Q elements, and you have a message. You have a message in this alphabet, which is A1, A2, A3, and so on. It may be long, and you want to do something to this, this message contains some information that is precious for you. Then you want to transmit this information or this message via a channel. So an important thing is a channel. And, well, let me do it other ways. So you have a transmitter device, a receiver device, and a channel here. Now, when we are speaking about a channel, you shouldn't just imagine the telephone line, though it's one of the examples. The channel may be in space, like telephone or internet. It may be as well in time. See, you put your information on the hard disk of your computer. Half a year later, you want to read it. The information is damaged. It's damaged because there are cosmic rays that hit it. There are technical inaccuracies and many things like that. Like there is noise as well in a channel, in a transmission channel. So you have some noise here. If you transmit this message, with high probability, 1, 2, 3 or many symbols will be changed and you'll be lost. So what to do? The idea is that you do some preliminary work and some work after the process, which is that instead of transmitting this message, you encode it. So code. You encode the message, and then you decode the message back. And this code should introduce redundancy into the scheme. And then you may decode it, hopefully without mistake. So on the practical side, there are different methods to do it, and I'll restrict myself to what is called block codes. So you take key symbols, and then the message continues, and you cut them out. So you cut it into blocks of key symbols. That is, that your message becomes a word, let me call it, see, A, in A to the power k. Now you take, you have a map from A to the k to A to the n, where n is greater than k. And instead of transmitting a word here, you transmit its image here. The image is longer, and therefore it has some redundancy, but the redundancy may be a silly one. So there are two possibilities to make a redundancy extremely silly. One is that you just add something to your message in a way that if your message is somewhat distorted, the resulting message is distorted as well, and you cannot recognize it. So that wouldn't be good. Another way not to do is, though it's very good in a sense, is that you take your message, then you repeat it again. After 100 of repeatings, you send it. Then the receiver looks, out of 100 it has, say 70 messages that coincide one with the other, and the receiver says, well, this is a good one. So this is good enough in sense you protect information, and very bad because instead of sending a short message, you send a very long one. So the idea is to achieve two goals at the same time. One is that not too large number of mistakes in this message should be possible to correct, and in the same time that n is greater than k, of course, but not too much greater. And so there is a natural parameter, two parameters you see here. In fact, there are three. The first one was q, but q is fixed forever. So you have the length of the message, the information length of the message, that I will call the dimension. And then you have another thing, which is the minimum distance. So you consider this an, let me draw it, as a metric space. So the metric is that the distance between 2 points here is the number of different symbols. So the distance from A to B is the number of AI that are different from BI. And so you take the minimum of this, the image of this map is a subset, some subset here, and you want that any 2 points in this subset are far enough from one another. So let D be the minimum minimal distance for A different from B, both belonging to the image of A to the K. So you have about such a thing. We usually say that it is an NKDQ code. The question is, you fix two, Q is fixed, you also fix two of the three parameters, and you want to get something good. Good means that if K and D are fixed, you want N to be as small as possible. If N and one of the others is fixed, you want the third one to be as large as possible, which is reasonable. Up to this place, it makes no sense to me, either as a number theorist nor as an algebraic geometer. So I need some extra structures. So now I'm going to introduce these extra structures. So first of all, the alphabet A, I want it to be a field. So it's a finite field of Q elements. Next, among all the possible codes, so what is a code? I haven't told you. So a code C is any subset in AN. And it has the parameters N, K, D, and Q. So what is K? K is the Cure logarithm of the number of elements in C. D is the minimum distance, and N is here. So a good example is that C is a linear subspace in FQ to the N. So that's already better. On the technical side, it's good because the engineer would ask you, what is, you say that we embed A to the K into A to the N, but how do we do it? So here the answer is easy. So if it is linear, there is a generator matrix, and so you just apply a K by N matrix to an element in AK to get an element in AN, and they love it a lot. Or from my point of view, this is an extra structure, and you should keep in mind the following thing. Then, since I'm now passing to mathematics from the purely engineering problem, I'm not bothering about the matrix, and therefore I'm not bothering about any basis in C. But I do have to fix a basis in this space because the distance depends on it. In some sense, the C should be very skew, not at all parallel to the axis of this space. But how to make it good, nobody really knows. And now, that's what a linear block code is for a specialist in coding theory. Now let me tell you what a linear block code is for me. So take a projective space of dimension k minus 1. Defined over Fq. So I take only Fq points of it for a moment. And inside of this projective space, I take a set X of cardinality N. Well, here, to be more accurate, I should say that, in fact, this X can have repetitions. which means that I'm not taking a subset here, but I'm rather taking, I take no. It may, the 2 points, we have n points in the projective space, but some of them may coincide.
So zero cycle.
Oh, yes, a zero cycle, an effective zero cycle. Or sometimes it will be easier for me to consider it as an effective zero cycle. Sometimes it will be easier for me just, I take a set of n elements, let me call it In, while not ordered, and then I map it into pk minus 1. So the image that may have multiplicities is what I need. Now, I call this a projective system, which is, of course, not a very good term, but I don't know any better one. You may say a finite projective system or whatever it is, but not to be mixed up with a linear system on a variety. This projective system has 3 parameters, just as a code has, or 4 if you prefer. So Q is Q, N is N, K is K. And I have to define D. So let me define D in the following way. N minus D equals, by definition, the maximum of the intersection X intersected with a hyperplane H. And the maximum is taken over all hyperplanes. So now the problem to find a good code becomes a natural problem in finite geometry, because I have hidden out all the bases. This projective space has no base at all. It's an abstract projective space over a finite field. The base I had here is hidden inside this set, this zero cycle. And the question is, in fact, so suppose for a moment that you are over an infinite field. Then you know what is a set of n points in a general position with respect to hyperplanes. That is that no 3 points are on a line, no 4 points on a plane, and so on. Now, here in a finite space, there are not enough points that you can achieve it. Because in an infinite space, if you are not in a generic position, you just take a point, you move it slightly, and you gain. Here you can't. So the question is, what is the best possible generic position for n points in a k-1 projective space over a finite field fq? Of course, if q is large with respect to n and k, then you can achieve anything just as in the case when the field is infinite. But here, the field is fixed once and forever, and n is usually pretty large, so no easy answer can be found. Now, why the left side and the right side are the same? So, first of all, that's not exactly true. Because on each side there are some degenerate cases. So here I would say that the code is non-degenerate if C is not contained in fq to the power n minus 1, meaning that the x's here are just parallel to the x's here. So it's not contained in a coordinate hyperplane. Yes, it's not contained in a coordinate hyperplane, which is natural to suppose, because in this case you just consider C as a code in a smaller space, and by definition this is better. So let me write it here. So what we want is n small, k and d large. Now here I would like to exclude a degenerate case as well, which is I wouldn't like X to be contained in a hyperplane. And now here I would say that two codes are equivalent if they're equivalent under the action of the following group. You can interchange the coordinates, which is the symmetric group of n elements, and also you can multiply each any coordinate by a non-zero number. So you have f q star to the n, semi-direct product with Sn. So this, yeah.
So your non-degeneracy condition for the right-hand side,
I don't repeat it.
In the non-degeneracy case for the right-hand side, H is required to be vary over the set of hyperplanes, right?
A non-degenerate case means that whatever hyperplane you take,
so you vary over
there is always a point out of it.
But in that maximum, H is also varying over the hyperplanes
right.
or over the linear subspaces?
No, or over hyperplanes as well. So H is a hyperplane. There is a generalization in that direction, but I'll maybe mention it later. But at the moment, everywhere H is a hyperplane. Yes, so here we also have a group acting on the set of these projective systems, which is PGL of K. So this is a group that, now you see it immediately that neither this group nor this group acting on a code or on a projective system influences the parameters. So NKDQ code will stay an NKDQ code. The parameters are the same. And here as well. And now the theorem, which is an exercise, in fact, an easy one, is that the classes of non-degenerate objects on the left and on the right are in one-to-one correspondence. So the idea to prove the theorem is that, let me just show you how you get one from the other. So you take a code C here. It is embedded in FQ to the n. So I take the pi I, let be the ith projection onto FQ. So I get a linear map from C to FQ, which is an element of the dual linear space. So now I take the projectivization of this dual linear space, which will be pk to the minus 1, and this pi be one of the elements of X. And vice versa. So you take X, you lift it in whatever way you like to an element in a linear space, in a k-dimensional linear space, and then you take the dual, and you get this map, and therefore you get your code C. So this is an exercise. Now, why this is good for me? Because now I see an immediate source of lots of codes, which is, so now I go out of here. Maybe I'll return to this definition from time to time, but not right now. So the now let X be just W of FQ, where W is an algebraic variety. So again, I have mentioned the multiplicities, which I need for this theorem to be true. So since I have mentioned the multiplicity, instead of just taking the W of FQ, what I take is I have an algebraic variety W, which is mapped into Pk minus 1. And I take the image and of its FQ points, and wherever several points are mapped into one and the same point here, I just see that I get a multiplicity. So instead of just considering the image, you consider the map. Now, so we have lots of algebraic geometry codes. But the question is that, first of all, that you need two things. You need a possibility to see what is the minimum distance. I presume, which is not true, that you know the number of points here, which is also a very good question, and about for an algebraic variety, usually we do not know it. But even if we know that, the question is, how do you estimate this d? And the answer is that it's very difficult. Now, to make this difficult thing easy, I suppose that this variety W is in fact a curve. And by abuse of notation, I'll call it X. Just so X is a curve. And if it is a curve, it lies in the projective variety. So you intersect it with a hyperplane. The hyperplane intersects if you are over an algebraic closed field. Then the hyperplane, and if you count with multiplicities, the hyperplane intersects it by the number of points, which is equal to the degree of this embedded curve. So let me write that n minus d just equals the degree of X in this projective space. Now, of course, this is not exactly true because, first of all, you are interested in a true intersection. You do not count multiplicities unless there are multiplicities that come out of the map from X to the space. Well, for a while, just suppose that will be easier, that X is a curve that is inside there and we have no multiplicities at all. It has n points. Now, other question is that, of course, a hyperplane intersects X not only over FQ points. There are points of higher degrees. And therefore, instead of having this, you have an inequality. This inequality saves you both from multiplicities and from the fact that your ground field is not algebraically closed. So now the next question is that I know lots of curves, but how do I embed them into projective varieties? That we know. So to embed a curve into a projective variety, I consider an abstract algebraic curve of FQ. I consider a linear bundle on it, or just a divisor. Let me say that it's a divisor D on X. And then you take the linear space of functions on X associated with this divisor D. That is that this divisor, you may think it is just that the poles of a rational function on X shouldn't exceed the multiplicity you have in this divisor. So L of D by definition is 0, and such functions f in fq of x star that the divisor of f plus d is effective. This is a linear space. Dimension is given by the Riemann-Roch theorem. So k equals small l of d, and we know it at least to be greater than or equal to the degree of d. So let A be the degree of d. So A minus g plus 1. There is some abundance here if A is not large enough, but it's positive. So you know k. Again, the question how many points do you have on X is a very good question. We do not always know how to answer. We know the degree of the this linear system corresponds to an embedding into this projective space. You just take a base here and you apply them to X. These k functions, you apply them to X, and you get something in pk minus 1. And so the degree d, or better to say n minus d, is the degree of the embedding, which is A. And now I know, in a sense, all the parameters. Here I'm maybe not going to see how good the parameters are, except for one point, that from this geometric description of a code, you can easily prove that some exercise as well, that k plus d is never greater than n plus 1. This is just that when we have an equality here, it is a general position. You can't do better. And here, if you add k and d, what you get is that k plus d is greater than or equal to n plus 1 minus the genus. That is that the larger the genus of the curve, the worse is the curve. But, so the best code you get is on the line, except for one restriction, that on the line you have about q plus 1 point. So you cannot get n larger than q plus 1. And if you need longer curves, then you are obliged to take curves of higher g. These curves happen to be much better than, so all this theory is due to an original idea of Valery Gopa, who had no knowledge of algebraic geometry, but had a very good knowledge of codes. So in his papers that have lots of mistakes and strange from our point of view expressions, there was an absolutely new and genial idea that from a code you can obtain a code. So he spoke in different terms. other my invention than his, but the idea is his. So the fact that these two notions are linked, that's the most important. The theory here is now nearly 30 years old. The original interest to it is due to the fact that, as we happen to show then, if you need curves with many points and with reasonable genus, so that n be large and g not too large, then you should take modular curves of different types. There are reductions into a finite field, and the modular theory gives you what you need. And the codes happen to be much better than a conjecture that, they're better than what people thought possible at the moment. So when the n is very large, yes.
So the FT rational points are the codes of variety.
Yes, yes.
Okay, so it seems to be independent of any divisor on your curve.
Yes, well, if your curve is already embedded, you don't need any layers. If you have an abstract curve, you have to embed it.
So these are divisor embedding an empty
This is
divisor.
the divisor that
Okay.
embeds the curve.
So very empty divisor. Okay.
These codes are good enough, and so that's why people in coding theory were interested in the theory. Now, why people in algebraic geometry and number theory were interested in it? The reason is that lots of questions we have about curves over finite fields, and then later on about number fields, and about varieties over finite fields and number fields, were not ever asked because the people were just thinking in a different direction. For example, so how many points can there be on a curve? So that's easy. So if you have a curve over a finite field, and then the number of points on it by Andrew B is given by the following formula. It's Q plus 1 minus the sum of omega i's, where these are the inverse Frobenius roots. So the sum goes from 1 to 2 times the genus. The absolute value of omega I is, by the Riemann hypothesis, square root of Q. Riemann hypothesis is proved, and also they go in pairs. Omega I is supposed to be equal omega G plus I bar complex conjugate. Out of this, what people tried to prove normally, they considered a family of curve stacks. Say you take one curve over a number field and different reductions. Then Q goes to infinity. Q goes to infinity, and the question is how close to Q plus 1 this sum is. And for high-dimensional varieties, this is Langevin theory. This asymptotics have no sense at all for codes, because for codes, as I have told you, Q is fixed once and forever. And the question in an opposite, in a perpendicular direction arises, which is that Q is fixed, G is very large. So how large can be M? And out of this, you get immediately that M is at most U plus 1 plus 2G square root of Q. So U plus 1 is small, and you divide M by G, and so asymptotically, you ignore this, and you get 2 square root of q. In fact, it can't be as large as that due to a very funny idea of Yasutaka Ihara. The idea is, suppose that the number of points is large, then omega i's are very close to the negative part of the real axis, because you want this minus this sum to be as large as possible. So your omega i's should be here or not far from it. Now, take a square. You take a square, and the square will be somewhere here on the positive side, which means that the number of points, if you take the same curve x, and you tensor it over fq by fq squared, that is, you consider, instead of considering it as a curve over fq, you consider it as a curve over fq squared. Then n2 will be q squared plus 1 minus the sum of omega i's squared and v again. And these omega i's are positive, therefore this sum is very much negative, and the curve cannot have a negative number of points. Neither can it happen that n2 is smaller than n1. So, because of this, this bound is not attained. We have a better bound, we call it Dritten-Fledder's bound, which is n over g is asymptotically not greater than square root of q minus 1. Many other questions of this type happen to arise starting from 1980s because of this new approach to curves over finite fields. Now, for me, just as for the most part of the audience, I think, a curve and the field of rational functions on it are of course the same. And morally speaking, that is more or less the same as a number field. So now the question is, suppose from a function field, yes, so here, let me repeat something. It's just that there are 2 ways to construct a code. One way is that I take this divisor D, I take the corresponding linear system, I embed by this linear system, I embed x into the corresponding projective space, and I take the projective system, which is the image. Another idea is that you can look at it directly from the definition of a code that I have erased. That is, you take this L of G, write it here. So you just take L of G, which is a k-dimensional space over Q, and you embed it by evaluating it in rational points. So let me do it like this. That let P be the set P1 and so on, Pn, and this be x of f2. Now you just evaluate each function here in a corresponding place, P1, P2, and so on, and you get a map into f3 to the power n. And the image of this map is a code. So it's one and the same code. So this is algebra in a sense, and that is geometry.
So your points should be outside of the support of the...
Well, that's a minor thing. As far as I said it, yes. But it's easily avoided. So In fact, it shouldn't. So, in fact, there is the following generalization of the construction keep in mind, which applies to any variety except that good curves will never yet get but from curves. So you have a variety CV and a linear bundle element L. Then you fix your set of points. It may be all points of V or some part of those. Then what you do is you take the sections of this.
FQ points.
FQ points. FQ points, of course, because there are again. I hesitate to say yes or no because you can generalize it taking points of higher orders, but for the moment, let us suppose that P lies in UFQ. Now, you take the global sections of this linear bundle, and you send it to, for each global section, you take its value in a point. So, of course, for a global section and a point, you cannot see what the value is. You can only see whether it's zero or non-zero. But what you do is that in an arbitrary way, you take, you just trivialize, that is, the fiber at your point Pi, you introduce a basis in it, and it becomes FQ. So it's not invariant, but up to the groups I was speaking about, it will be invariant. So you trivialize your bundle at each point, you take the value, and this construction says nothing about the fact that the support of your device is joined from points. So that's one way to avoid it. Another way is that you just take local parameter. If your function has a pole, you divide by this local parameter to the order of the pole. So that's an elementary way to overcome the symptom. So, but to make it easier for understanding, let us suppose that the support of E is disjoint from the set. So, and now, now that we know that we get indirect curves from algebraic curves, the question is, what is the number theorem analog? Here we are somewhat in trouble.
I did not understand how you will evaluate.
Well, I just think this is a well. Let me draw it. So this is a linear bundle. So this is a point. This is a section. And what I know is that this is a zero section. Now I take this fiber. It's one dimensional. I choose any vector on it, which I call 1, and then this fiber becomes isomorphic to FQ. And so the value here is the ith coordinate. So if this is Pi, then the value here is ith coordinate of this map.
But it depends on the choice of the...
Yeah, it depends on the choice of trivialization.
Okay, the other way would be to trivialize x and then
sure.
And then to trivialize on open sets of x, so take hyperplane sections of them.
Right.
Is that the same, more or less?
It should be.
So you pull back, you take it.
But anyway, what is important that, in fact, when I'm speaking about codes, and code is the image here, I always allow to multiply any coordinate by a non-zero constant, and also to interchange coordinates. So if you take a different trivialization here, that will be the action of that group. Nothing. There are many equivalent constructions of this you can play with. Yes, with number fields, we're in trouble because now let me repeat the same construction. Let K be a global field. Well, for a moment, let it be a function field that corresponds to x. It has some places. So it has a set of places. Out of this set of places, well, and is a set of places. Now here I choose a finite number of places that I call P. Now what I do is I take this K, I embed it into the product, not as I would do for an adelic construction where this product is taken over all places, but into a finite product over P of KV, where P is a valuation that corresponds to a point in P. Now, I take an advantage from the fact that this KV, that if each point here is of degree 1, then KV is just Laurent series over FQ. So KV equals F. And so then what I do is that I just take the constant term, or better to say, if it is a Laurent series, I take the first term of it. So this is first term of a Laurent series, and this first term is an element of FQ. So I get here FQ to the power the number of places in. And so this is another.
Just a quotient map by the maximum.
Yes, just a quotient map by T, it's by the maximal idea. Now, if I take the through map here, I get nothing good. But later, so inside of K, I take something, which in my case there was the space associated to a divisor. And I take the through map of all of it. And so that's this construction here. Now, suppose I want to do the same for a number field. So what problems I'm going to encounter? Well, lots of. First of all, there are not many enough places of the same characteristics. Of course, there are some, but generically speaking, this KV will not be isomorphic to one another. Then there are infinite places, Archimedean ones. What to do with those? And the last, so I'll get something in there, but it won't be a code, it won't be anything. So what is the sense in not doing all that? So Hendrik-Lenstra, find out. Yeah.
So the Q in the FQ to the hash key, that does not have to coincide with the Q of the basically FQ, right?
You may presume it. It's avoidable.
Okay, so you assume that at least one place of P has residue field FQ and not an extension.
No. In that particular case, I presume that any place inside of P is of degree 1. That is, the residue field is of P. if I do differently, the construction passes through, but I have a problem in evaluating the distance because the map won't be in FQ to some power. It will be to rather in product of FQ to some powers. So here I'm happy it's FQ to that, but otherwise it will be say FQ to the m times Q square to the m2, and so on. And then to get a code, I have to choose some basis in FQ square, and then I'm in trouble. You just believe me that I'm in trouble. Something can be got out of it, but not too much. So with number fields, it's even worse. And well, I think it's 3 o'clock. So what I do is I just announce what I'm going to say, and I will read it next time. So there is an idea of Andrew Klanstra that says that you can get a code out of a number sheet, but this code will be neither linear nor beautiful. But nevertheless, its parameters will be very good, just almost as good as for a function field. So to do that, you do some ugly things, like you get different elements of your so you are not in FQ to some power. You are in product of different FQs. So what you do is you take the largest Q and you say that let me embed FR into FQ just as a set, and suppose that nothing is repeated, or well, I'll speak about it next time. So, thank you.
Questions?
At least. I should have done it 1 hour ago. Yeah.
The Gopa codes, the P is on a variety of higher dimension than code.
If I use a variety of higher dimension, well, what happens is, suppose you have a surface. So you and suppose that you're lucky enough it is already embedded. So you embed it, you cut it by a hyperplane. If this hyperplane is in a generic position, it cuts it over a curve. And this curve is presumably irreducible. Then you can at least estimate the number of points on it. But the hyperplane needn't be in a generic position. So it intersects it in a highly degenerate curve, which may be a union of lines. It have lots of points that spoil the code greatly. The idea would be that there is a generalization that instead of considering hyperplanes, consider planes of codimension 2. But again, if it is not generic, it can cut it over a curve again, so you are lost. So you get some information, but much less than for curves.
More questions? Thank you.